everybody. We are starting our plenary session. So we have been thinking that it would be interesting in this conference to have a talk about the geochemistry of the future worlds, that is, of the exoplanet. So maybe we should call it exochemistry or whatever. And so our morning speaker is Franck Selsis. Franck is a CNRS researcher at Observatoire Astrophysique de Bordeaux. He has been working for long on modeling the atmospheres of exoplanets, not exoplanets first, but on planets from the solar system, including the early Earth. And he is more and more interested in the detection of exoplanets and how we could be able to do some chemistry and to understand those exotic words. So I leave the word to Franck.
So, thank you very much. Thank you for being here that early. And thanks to the organizer for inviting me here to give me this opportunity to attend this amazing event in this amazing city. So the room is very impressive, although I think it seems that we could have used a smaller one, but let's do with this one. So, so before I start by showing you the current catalog of known exoplanets, let me tell you a few words about how we detect them. So I will only spend one slide on that because it's not really my field. And I will only describe two of the methods, the two methods that have been the most successful. There are other ones, but these two ones have been the one that have given us nearly all the current exoplanets. So the first method is called the radial velocity method. So the idea is to measure the velocity of the star by taking advantage of the Doppler effect. So what you're doing is you're doing high-resolution spectroscopy of the star, and you're monitoring the star night after night, and you're looking at the displacement of the line of the star and to measure the vitesse, to measure the velocity. So what you want to measure is actually this motion, the motion of the orbital motion of the star that is due to the presence of a planet. So it's an indirect measurement. So, and this is the kind of signal you're looking for. You're looking for a periodic variation of the velocity of the star projected on the line of sight. And if you see some periodic variation, you have detected the planet. And when you have detected the planet, you have the orbital period of the planet. As you have a good estimate of the mass of the star, you also know the orbital distance of the planet. And you have an estimate of the mass, you have a measurement of the mass, actually not the true mass, but the mass multiplied by the sinus of the inclination of the system, which is not known. So this is the kind of curve that you get. And this is an example for this given planet, which is a planet that's slightly more massive than Neptune, and at a very short period of 2.5 days. So many of the exoplanets that we know have very, very short period. They're very hot. And when you do that, you can also measure the eccentricity of the planet. And many of the exoplanets are not at all circular. They have very high eccentricities. So this is one of the technique. The other technique is that for a small fraction of the exoplanets, we are lucky enough that we can see the planet passing in front of its star and producing what we call a transit. So in this case, what you have to do is to do a photometric monitoring of the star and try to detect this dip, this transit, which happens when the planet is in front of the star. And this is a very interesting method because it gives you, of course, it gives you the orbital period. It's the time between two transits. So again, it gives you the orbital distance. And also, the depth of the transits give you the radius of the planet. And because the planet is transiting, you also know the inclination of the system. It has to be close to 90 degrees, right? The observer is roughly in the plane of the orbit. So, and when it becomes very interesting when you apply both methods, because these ones give you the mass, this one gives you the inclination and the radius, so you have the true mass and the inclination. So when you have both, you can really start to do physics of these planets, because you know the density of the planet, you can put your planet in a mass radius diagram, and you can compare with theoretical curves. So you can test if your planet is made of rock, iron, ice, or mainly gas. So that's you can see that we're already starting to do composition and internal structure of exoplanet just with these measurements. So this is part of the current catalog of exoplanets. So we could spend half an hour just describing that. There are so many information in that, but I will try to be brief on that. So what do you have here? So you have here the mass of the planets, or actually the mass times the sinus of the inclination for those which are not transiting, and we don't know the true mass, but just the minimum mass. And here you have the orbital distance. So the planets that have been detected only by radial velocity are the blue dots, and the ones that have been detected also by transit are the one with the red circle. Okay. This line, it gives you roughly the precision that we have currently in measuring the amplitude of the radial velocity variation. So it's about 2 meters per second. We can measure an amplitude of 2 meters per second. Actually, the best precision that was ever done on measuring the velocity of a star was about 30 centimeters per second, which is about this velocity. So that's quite impressive. So you can see that most of the planets that we know are above this line. And little by little, when the precision is getting better, we will unveil the population that is below this line and where the Earth, an analog of the Earth, will be found. So, yeah, at the exception of a few, all these planets have been also measured by radial velocity, except, for instance, in this case, you cannot measure the mass by radial velocity, but I will explain you later how it was done. So it's only part of the current catalog of exoplanets, because there is another very successful observatory called Kepler that was launched by NASA that has detected more than 1,000 exoplanet candidates. The problem here is that Kepler is monitoring very distant stars and is looking at transits, and it's very difficult to do radial velocity measurements on these stars. And it will take time, and for some of them it won't be possible. So there are still candidates. If you pick one of these dots, maybe it's not a planet, maybe it's an artifact. But statistically, most of them are planets. And you can see that Kepler is able to find planets that are smaller than the Earth. This is about half the radius of the Earth. So the very interesting thing here is that these big planets here that have the size of Jupiter, they are the easiest one to detect. But you can see that when you go to about the size of the Earth, there are many, many, many more planets, although they are much, much more difficult to detect, which tells you that there are much more terrestrial planets than giant planets. There will be really a lot of Earth analogs in the Milky Way. So most of these are candidates, but in some cases, the systems are many planets, and actually the majority of planets are in multiple systems. And when Kepler is discovering multiple systems, like this one, actually by looking at the variation in the time of the transits, you can see the planet-planet interactions. So you can be sure that these are planets, and you can even determine the mass of the planets because of this planet-planet interaction. A little bit like when Neptune was inferred from the motion of the other planets. So this is the same kind of calculation. In this case, you don't need the radial velocity measurements to be able to estimate the mass of the planet and to be sure that these are planets. So it's a very nice animation. So that this time steps is 1 day, and this animation is covering the whole Kepler mission, which is a few years. And you can see that although these are preliminary results, there are already plenty of extrasolar systems discovered. So I have this slide, which could be my conclusion, but I am always afraid that I will not go through the whole talk, so I prefer to put it there. So there was a very nice story in the exoplanet business. Is the fact that, well, somehow the planet formation model and the models of the early formation and the early evolution of the solar system were kind of stuck before the detection of exoplanets. And with the discovery of all these very different systems that were, how could I say, pointing to processes like planet migration, planet interaction that were not well known before the discovery of exoplanets, well, this was a kind of revolution that allowed the scientists to really understand how the solar system formed and evolved. So by looking to exoplanets, they were able to understand much better the origin of the solar system. And you may think that developing a model that should explain the formation of the solar system is easier than developing a model that should explain not only the solar system, but all the exoplanet system. Should be more difficult. Actually, it's easier to describe all the systems. And my conclusion, I think, is that we can expect the same kind of revolution in the field of exoplanet atmosphere. By looking at the atmosphere of all these exoplanets, we will understand much better the origin of our atmosphere in the solar system and the origin of the Earth's atmosphere. So if you are interested in these guys, you should really keep an eye on exoplanets. So first, I will talk about these planets that we call the hot Jupiters, and that were the first to be detected because they are the easiest one to be detected. Although they are very rare, actually only one star in 100 have one of those, but they are the easiest one to detect, and these are the ones for which we have currently data on atmospheres. So these planets that have the size of Jupiter, but are much, much hotter. So how can we get information on the atmosphere? So this is done in one case only. It's when the planet is transiting. So when the planet is transiting, so this is a very, very nice observation done by Knudsen et al. In 2008, where they monitored, they did a photometric monitoring of a star during the whole orbit of the planet. And it's a transiting planet. It's AG 189733. It's one of the closest from the sun of these hot Jupiters. So what you can see here is the primary transit. It's when the planet is in front of the star. And this produces a dip of about 2% of the luminosity of the star. So when you have a transit, let's first assume that you have no atmosphere. If you have no atmosphere, whether you're looking at the transit in the UV or in the visible or in the infrared, the depth of the transit is just determined by the radius of the planet, and the radius of the planet does not change with the wavelength. So you should find a transit depth, or let's say an apparent radius of the planet that is independent of the wavelength. But now with the planet as an atmosphere, the opacity of the atmosphere will change with the wavelength. So actually the apparent size of the planet will change with the wavelength. And it will be shaped by the optical properties of the atmosphere. So if you look at the wavelengths where the atmosphere is very opaque, you will have the impression that the planet is bigger than at another wavelength. And this has been done. This has been done for some exoplanets, and this is the kind of spectrum that you get. So this is the wavelengths from visible to mid-infrared, and you can see the change in absorption, so you need to have very, very accurate observations. And this is the theoretical spectrum that was predicted, and it's actually completely shaped by the water vapor absorption. And this is what is actually seen. So we can, with this kind of measurement, we can probe the composition of this atmosphere. So another way to probe the atmosphere of this planet is to study it at the secondary eclipse. The secondary eclipse is when the planet disappears behind the star. So when you do a measurement before the planet disappears and when it disappears, the difference between the two is the thermal emission of the planet. So by making the difference between the two, you get the thermal emission of the planet. So if you do that at different wavelengths, like that, so we're at 3 micron, 4, 6, 8, 16, 24. This was done with Spitzer, a small infrared telescope in space. And you get a spectrum of the thermal emission of the planet. So this is an example of what was done. So this is a synthetic spectrum. This has the data point. And this is another example. So it means that it's very interesting to model the chemistry in this atmosphere, so which is what we do. So I won't go into the details. This is, for instance, a simulation of the composition in 1D, the composition of one of these hot Jupiters. In this model, what we put is about 1,000 of chemical reactions, about maybe 100 of chemical species. We take into account the very strong UV flux, which is 10,000 times stronger than the one at the Jupiter distance. So there is a lot of photolysis going on in this atmosphere. There is some mixing, there is some molecular diffusion. And for each of these compounds, you have two lines. One is the one that is predicted at the chemical equilibrium, so where the composition is only given by the temperature, and the other line is given by this model. And you see that for this planet, there are not big differences because it's so hot that it's nearly at the equilibrium. But we do have a problem. These models, they don't reproduce well the observations. So we don't know if there is a problem with the observations or with the model. I cannot talk about the observations, but I know that we have problems with the models because actually these planets are quite complex. And the problem is that we have this 1D description of a planet while there are very important 3D processes in the planet, and I will try to illustrate that. So what you see here are maps, temperature maps, and wind maps. So you don't really see the little arrows that represent the winds, but you can see the colors that show the temperature. So you have latitude, longitude, and this is at 3 different pressure level, 1 bar, and this is a 1 millibar. And this was done with a very simple circulation model that should catch the main trend in atmospheric circulation for this model. And if you look at the range of temperature that you have, for instance, at this level, between about 900 K and nearly 2000 K, actually, if you do some chemical equilibrium calculation, so this square is the range of temperature that you find in this planet, you will see that depending on the temperature, you have very different chemical regime. If you're cold, for instance, the carbon will be mainly into the methane, while when it's a little bit hotter, it will be mainly into the carbon monoxide. So actually, if you do chemical equilibrium calculation, the composition here will be very different from the composition here. But the problem is that actually, if you look at the time scale for chemical evolution, so if you go from one of these temperatures to another one, it takes more time for the chemical system to equilibrate than the time it takes for a cell of gas to cool or to warm. So it means that it's never actually in equilibrium. It will be quenched by high temperature, and it will be very complicated to model. You will really have to couple dynamics and chemistry. So that's one of the problems. And the other problem is related with the way we observe this planet. So if you're getting information by doing primary eclipse spectroscopy, you're probing this area, right? The limbs of the atmosphere. So if you're doing that, you're looking at this specific region. So in one case, it's the sunset, and the other case, it's the down, and you're looking at equatorial region and polar region. So you're mixing in the same data set regions of the atmosphere that should behave completely differently. So chemistry and 3D dynamics must be coupled. It's not done yet. It will be very difficult because we have thousands of reactions, but it should be done in the future. So that was for, I'm not going to talk much more about this hot giant planet, these hot Jupiters, because I'm more interested in terrestrial planets. I would not dare to call them Earth-like planets because they are probably very different from the Earth, because the one that we know are of very short period. You can see that on these diagrams. These planets that have a mass of about 10 Earth masses or less should be very different from the Earth. But the good news, as I told you before, is that they are very, very frequent. Actually, this population of planets here, you found these planets around about at least 1/4 of the stars that you're looking at. So every 4 stars you're looking at, you find one of those. And these are actually pretty big compared to the Earth. And we believe that if you go to smaller planets, this fraction will increase. So this is really, really a lower limit on the abundance of planets. So there will be an overwhelming amount of terrestrial planets out there. And these planets, they must have an extraordinary diversity. If you look at the solar system, you already see a diversity in the composition of the atmosphere of the terrestrial planet, Venus, the Earth, Mars. They are very different, but the diversity is is going to explode with this one. And we already see this diversity, because for these few planets that do transit and for which we have both a mass and radius measurement, we can put them in a mass radius diagram, right? And compare with so we can compare that with theoretical mass radius relationship for planets made of pure iron, pure rock, or pure ice. And you can see that there is a whole diversity. You can find planets that have the same mass, about the same mass, but a factor of 2 different in radius. On the contrary, you can find planets that have the same radius, but a factor of 2 difference in mass. So some planets will be probably similar to a big Mercury, and some planets will be similar to a big Neptune, and probably big Neptune that has lost his hydrogen atmosphere, but which is made of half ice and half rock. So you can imagine what kind of diversity this would produce in terms of atmosphere. So what I'm going to show you is some modeling we have done to start little by little to explore, to model, to explore this type of atmospheres. And I will show you 2 examples where we have made some 3D model of the climate of some planets, really to try to start to explore the kind of weird climates and weird atmosphere we will have there. And in order to do that, we have developed a climate model. So this has been done with the people of the laboratory of dynamic meteorology in Paris. And I mention that because I think it's very important to have people who have worked on solar system planet or in Earth science to work on exoplanet. You have to realize that at the moment, most people who study exoplanets, so who are doing planetary science around other stars, are astronomers. And most of them have a background in stellar physics, stellar observations. And we would very much benefit from the input of people coming from Earth science and solar system planetary science to study this subject. And this is what these people did there. They realized that all their tools and knowledge on the atmosphere of the Earth, Mars, Venus, Titan could be very well exported to extrasolar planet field. So during the last 2-3 years, we developed a kind of versatile, I would not dare to call it universal because it's far from being universal, but versatile 3D model. And the novelty with this model is that the real difficulty, if you want to have a model that is able to model different types of atmosphere, is the radiative transfer. If you look at global climate models, 3D models that have been developed for Mars, the Earth, etc., they have a very specific treatment of the radiative transfer, which is optimized for this composition for this planet. And here we want to be able to change the atmosphere and to change the star, and still to be able to do that. So we change completely the philosophy of the radiative transfer. So whatever the atmosphere you want to model, we first do a series of high-resolution spectra for different pressure, temperature composition. From these high-resolution spectra, we compute band parameter, what we call K-correlated coefficients, in about 80 bands. So 80 bands, it's very low resolution for observers, but it's very high resolution for this kind of atmosphere models. And actually, usually for exoplanets, we don't have very high resolution. So a resolution with 80 bands is actually pretty good if we want to reproduce observables for exoplanets. So then our model can be used in 1D, and then you get a one-dimensional radiative convective code, and then you can run the full 3D model if you want to study atmospheric circulation and stuff like that. So the good thing, what we like with this model is that you can study climate just for them to learn about exotic climates around other stars, but also you can simulate observables. You can simulate the flux that you are expecting from this planet. And in principle, this scheme should work for any atmospheric species, provided that we have the basic data to describe them. So the spectroscopy and the thermodynamics. Sometimes we are lacking them. But I will show a very simple example. And the first example I will show you is, there is a question that we have for some time, And we have a problem with transiting planets. The transiting planets are very rare. And because they are rare, they are far away. And if they are far away, it's difficult to characterize this object because they are too distant. So for randomly oriented system, the probability that the planet transits is the radius of the star divided by the orbital distance. For this population of hot terrestrial exoplanets that I've shown, typically the transit probability is 5%. So about 25% of the stars do have at least one of these planets, and the transit probability is 5%. If we consider a sphere of 10 parsecs, it's the unit that we use in astronomy, it's 3.2 light years. If we consider a sphere of 10 parsecs around the sun, there are roughly 300 stars. So which means that there should be about 75 of these big hot terrestrial planets. That's already a big number to start to do some comparative planetology, if you think about it. But if you consider only the transiting one, statistically there should be 3.75 only, and that's that's less interesting for doing characterization or comparison. So, is there a possibility, in the absence of huge telescope that we may have in the future that will be able really to separate the star and the planet, can we, just by using the current technique or the forthcoming generation of observatory, can we study planets that do not transit but are very nearby? And the answer is maybe, because if I come back to this, to this plot, in addition to the two transits, the transit and the eclipse here that we see, you can see this trend here. You can see that it's not a flat curve. And if you do a close-up here, you can see very well that there is an increase of the planetary signal due to the changing of the phase of the planet. So when you have the primary transit, what you see is the night side of the planet. And just before and after the secondary eclipse, what you see is the day side. And because these planets are hot, the time scale for radiative cooling is very short, so there is a significant difference between the temperature of the night side and the temperature of the day side. And this is what you see here. You see the difference between the day and the night in this data. And the thing is that if this would not be a transiting planet, so you would lose these transits, you would lose this absolute reference, that is the luminosity of the star that you get when the planet disappears, but you would still see this modulation due to the planet. So how could we use this modulation to characterize the planet? So, and I should tell that this has been observed in non-transiting configuration for some hot Jupiters and at least for one transiting rocky planet. So it's doable. So what I've been doing is that I've created this virtual planet right in the middle of this population, and I've assumed completely arbitrary an atmosphere. I assumed an atmosphere made of CO2, and I did the 3D modeling. So it's a very simple case. It's a large rocky planet of 1.8 Earth radii. It's around a small star, a red dwarf. It has an 8 days period. It's on a circular orbit. I assume it's tidally locked, so it's always showing the same face to the star, which is very consistent with the previous parameter. I assume only one atmospheric constituent as a first test, and I would have no clouds. I could have clouds in the model, but this is too hot for CO2 condensation, and I don't have water, and I have no dust, no aerosols. And I tested with no atmosphere, 0.1 bar, 1 bar, and 10 bars. And the idea is to see what kind of atmospheric circulation do I have, and what kind of phase modulation do I get. So first, with no atmosphere, well, it's easy. What you have here is how the planet looks like. So I assume an inclination of 60 degrees, which is the median inclination for randomly oriented system. And you have here 3 wavelengths, and one is a very strong CO2 band. And these are on the edge of this CO2 band. So of course, if you have no atmosphere, what you just have is you have the surface in radiative equilibrium, and that's like a big Mercury or a big moon. That's very easy to model. If you add an atmosphere, well, in these atmospheric windows, there is not much difference, but in the CO2 band, you cannot reach down to the surface, and what you see is the temperature of the atmosphere. So you don't have the same behavior with 0.1 bar. And if we increase the pressure, this trend will, of course, be more and more visible. So we start to see no variation at all in this CO2 band because we are probing the high atmosphere where circulation make all the atmosphere homogeneous, while in these windows we still probe down to near the surface. And if we increase the pressure to 10 bar, then we start to have some homogenization also in these two bands. So if I now do, so this is the same for one given wavelength and three pressure. So if I look at the spectrum, this is how it behaves. So you don't have one spectrum for this planet. The spectrum is going to change with the phase of the planet. If the planet is not transiting, you cannot get the absolute flux. You have always this combined star plus planet light. But what you can see is the variation. You can see the modulation. You know the period of the planet. You can filter everything else and just get the variation that are due to the planet. And if you plot that, so the blue spectrum and the red spectrum are the spectrum at the maximum of the spectrum and the minimum of the spectrum. So when you see most of the starlit and most of the night side. And the dashed line is the variation spectrum. It's the one that you can measure. And you can see two things. First, it's very similar to the day-side spectrum, and it's shaped by the molecular band in the atmosphere. So actually, by doing this kind of measurement, you could detect molecules even for non-transiting planets. And is it possible to do that? Yes, we did the numbers. It's doable with the James Webb Telescope, if it's hopefully launched. And another mission that has been accepted, preselected by ESA, ECO. And with this technique, we should be able to distinguish planets that has no atmosphere at all, like big Mercuries, from planets with a dense atmosphere. We can detect molecular features, and if the planet has no atmosphere, I did not talk about it here, you can measure the radius of the planet, you can infer the inclination and thus the true mass, and you can get the albedo of the planet. And to finish my talk, I think I have 5 minutes left or something like that. To finish my talk, I will describe another application of this 3D atmospheric model to this planet, this little dot here. It's a very interesting planet. So something I forgot to tell you is that in this plot, the size of the dot is proportional to the mass of the planet. So the bigger dots here are stars of about 2 times the mass of the sun, and the smallest one have about 1/3 of the mass of the sun. These are M stars. And this planet, which has a 68-day orbital period, well, if you compare in terms of orbital distance to the Earth, it seems pretty hot. Actually, it's much colder because it's around a very faint star. And what I'm going to show you is that the only planet, only one within this confirmed planet that is potentially habitable. So this planet is called Gliese 581d. It was discovered by the group of Michel Mayor and Stéphane Udry in 2007. And what I represented here is so you have the orbital distance, you have the stellar mass, so the sun is here, and this star is here. And this blue area is roughly what we call the habitable zone. It's the range of orbital distance where a planet can have liquid ocean. If it's too close, it's too warm and the ocean is vaporized. If it's too far away, there's no way you can have something, you can only have ice at the surface. In this region, you can have liquid water. And from a 1D modeling, we knew that this planet should be near the edge of the habitable zone. It should potentially be habitable. So we did more accurate modeling. So first we started with 1D, taking into account the real spectrum of the star, which is it's a key parameter. And actually, if you would model the same planet receiving the same amount of energy, but from sun-like stars, you can see that there is no habitable solution. So what you have here is the surface pressure in bar for a CO2 atmosphere, and this is the surface temperature you get in 1D. And you have to be above this line in order to get liquid water. And if you start to increase the pressure for a sun-like star, after about 1 or 2 bars, the CO2 would start to collapse. It would be too cold even for CO2, and there is no way you can build up a CO2 atmosphere. But around an M star, because it emits mainly in the infrared, The albedo of the planet is different. There is much more absorption by the atmosphere, and you can build up an atmosphere. You need about 10 bars of CO2, and then you reach habitable condition at the surface. Then if you add the water, so you assume that you have water at the surface, so which is this case, and you assume that there is a saturation of, the water is at saturation at the surface, so you have a relative humidity of 1 at the surface. You can even get pretty high temperature. So we were very happy with that, but we were concerned by the fact that this planet, because it's close to a star, it's tidally evolved. It's subjected to very strong tides, and this affects very much the rotation of this planet. So it's an eccentric planet, so it's very difficult to predict what the spin orbit, the spin of this planet will be, but we know that the obliquity is likely to be 0, so no season on this planet due to obliquity. And also, it has to rotate very slowly. And one possible configuration is that it is a 1-to-1 spin-orbit resonance, so synchronous state, like the Moon to the Earth, so showing always the same side to the star. It could be in another state, but this is one of the possible resonance. So is a dense CO2 atmosphere really stable on the planets that has a permanent dark side and very, very cold polar regions because of 0 obliquity? So we did the simulation, and the answer is yes. The answer is yes. So this is the worst case scenario, tidally locked, always showing the same face to the star. And you can see that with this very dense atmosphere that is able to make the planet very homogeneous, we get some habitable condition all over the planet. And of course, it works even better if you have rotation. So I'm about to finish. These are the results that we got in 3D. So this is for a rocky planet with little water on the surface, and this is for an ocean planet, really made of water. And this is the kind of temperature we got. So the range is the range of temperature we got in the 3D model. And so the conclusion is that yes, there is another potentially habitable planet in the catalog of exoplanets. We can model the spectrum that is associated with this modeling. I have to say that the atmosphere we assume is completely arbitrary. We assume something like that is Earth-like. CO2 as a greenhouse gas, water vapor, nitrogen. But it's to you geochemists to tell us what should be the real type of atmosphere we should consider there. It's completely arbitrary at the moment. But my conclusion is that in addition to the Earth, there is another planet which is inside the habitable zone of its star. And what you have to realize is that this line is going down, and it's going to unveil much more many of these planets. And actually, I will finish on that. This is the same catalog of exoplanets. This is the mass of the planet, this is the mass of the Earth, and this is the date of discovery. And it's very tempting to draw this kind of line and to see that, well, it should be tomorrow that we found an Earth mass planet. Thank you very much.
Thank you, Franck. We have time for a question. Please use the microphone. There are some microphones here.
Yeah, Burkhard Mölitzer, UC Berkeley. Thank you for the nice talk. I have an ozone question.
Yeah,
the Earth atmosphere temperature profile is dominated by ozone, which requires photochemistry. And as far as I'm aware, all the models that do exoplanet atmospheres assume thermodynamic equilibrium, so ozone cannot exist. Can you just explain that fact a little bit, if it's true, or if one has gone beyond these simple models?
No, it's not true that all exoplanet atmosphere models assume equilibrium. There are two types of, I would say there are two types of models. The one that are derived from stellar model, because as I said, exoplanet atmosphere are studied by astronomers, and they are used to use equilibrium model. So hot Jupiters that resemble a little bit brown dwarfs, they are very often modeled as equilibrium atmosphere. But when you model Earth-like planets, usually you do photochemical model. So I did that, for instance. I took an Earth and I put it around another star with the same composition as the Earth to see how the ozone layer changed and how the signature of the ozone changed. So, but when you do that, you have to assume a background composition of the atmosphere. So if you want to model an atmosphere, and if you're going to have ozone, you have to assume that there is oxygen in the atmosphere. And so you have to assume an oxygen-rich atmosphere, and then you can model how the ozone layer will change with changing composition, changing biogenic flux at the surface, changing stellar radiation. And we did this kind of study. There are quite a lot of papers on that. So all models are not assuming equilibrium.
Okay, thank you very much, Franck, for this very nice talk. We have to move on now for the award ceremony, and we thank the speaker again.